Okay, let's start now. So this is the 8th lecture on history and literature and math science, jointly organized by CMSA in Harvard and YMSC in Tsinghua University. So today will be chaired by Professor Baowen Fu. Okay, let's start.
Okay, we are happy to have Professor Kawamata lecture here. Professor Kawamata has made many important contributions to algebra geometry, especially in the minimal model program. He has also done a lot to promote algebra geometry in East Asia, for which we are very grateful. Today, he is going to lecture on Codara and complex manifolds. Okay, please.
Thank you very much for a nice introduction. And I'd like to thank organizer, especially Professor Yao, for inviting me to speak here. So in this talk, I'd like to review Kunihiko Kodaira's work on complex manifolds. So the plan of the talk is as follows. So first I recall his chronology, and then I'll speak on three topics: harmonic analysis, deformation theory, and compact complex surfaces. And this corresponds to each volume of 3-volume Kunihiko Kodaira's collected works. So that's very big and thick books. So actually, I did not read all of his works, but I learned a lot from his works also. So this is his chronology. So he was born in 1915 on March 16 in Tokyo. And he graduated from Math Department of the University of Tokyo in 1938. And then he entered the Physics Department and graduated in 41. So that was wartime. Yeah. So there was long war. And so I don't know what happened exactly, but so anyway, he spent more years as a student at that time. And he also studied physics also. But at that time, physics and mathematics are not so totally separated. So the interaction was much closer at that time. And he became, so after graduation, he became assistant professor at Tokyo University of Education. So this is not the University of Tokyo, but it was a kind of normal Tokyo Normal University. And so Tomonaga was a professor there. So Tomonaga is famous for renormalization. And so, after 2 years, he became assistant professor at Physics Department of University of Tokyo. But the war was becoming worse and worse. And so in 45, Mathematics Department and Physics Department evacuated from Tokyo to Nagano Prefecture. Nagano is Kodaira's ancestor's place, and Kodaira helped a lot in this evacuation time. And he saved a lot of books at the Math Department. So we still have old books at the Math Department, and that is due to his effort. And after the war, so it was quite poor. So he went to United States. But before that, he got a PhD from University of Tokyo, and his advisor was Shokichi Iyanaga. And it is harmonic fields in Riemannian manifold. So at that time, PhD was not so important in Japan. So you know that maybe, so I guess that he needed the degree before going to America. And he was invited to Princeton Institute in 1949. And after 3 years, he became associate professor at Princeton University. And 2 years later, he got Fields Medal. And 1 year later, he finally became full professor at Princeton University. But after 7 years, he moved to Johns Hopkins University. And 3 years later, he moved to Stanford University. So he moved to a lot of places. So maybe this is standard in the US, but not so standard these days in Japan. Okay, so that was maybe good. So most of his Kodaira's paper were written during that period. So in the wartime and also after the war. And in the wartime, the communication with the world was cut. So he could not read papers published abroad, but he developed his original ideas during that period. And so he said that it was good for developing original ideas. So after that, he moved back to Japan. So after 3 years in Stanford, so he went back to Japan in 1968. And he said that he was very shocked that the first salary was so small compared to the time in United States. So University of Tokyo did not, so it gave Kodaira the regular salary of professor. And at that time it was much smaller compared to America. But it was not so important to Kodaira, but more important thing was that there was no entrance examination at the University of Tokyo in 1969. It was a big news. So there was a student movement at that time, and the student occupied buildings of the university. For example, the main building, clock tower, was occupied by students, and also students refused to take classes. So there was no regular classes at that time. But still, Kodaira gave beautiful lectures to graduate students at that time, and some of them left as lecture notes. So I will talk about this later. So, and I studied algebraic geometry using his lecture notes. And still was, so he became involved in university politics. So between 71 to 73, he was elected as a dean of faculty of science, and he had to work hard for this university politics. And so only 7 years after becoming professor, he retired from University of Tokyo. So it is mandatory at age 60. And he moved to Gakushuin University. It is a small private university. And after 10 years, he retired from Gakushuin. And after retirement, he served the mathematics community as the chairman of ICM Kyoto. And he was a very successful fundraiser because he had a lot of top business people in his friend, because he was a graduate of University of Tokyo, and at that time, many of them become leading businessmen. And he died in 1997 at age 82. So this is his chronology. And I became graduate student just when he retired from Tokyo University. But still, I had a lot of chance to talk with him after that. Now, I'd like to explain mathematics. So Kodaira's object of mathematics is complex manifolds. So, and the motivation, Kodaira's motivation was to generalize Weyl's the book, the concept of a Riemann surface to higher dimensional case. So, actually, Codara said once like that. So I write here, and so the object is not necessarily algebraic manifold, and not even Kähler. So the method is restricted. So he used a lot of analysis. So since there are no ample divisor, so the induction on dimension is not possible. So if there is ample divisor, then you can cut by hyperplane section and reduce dimension by 1. Or not only ample divisor, but for general divisor, you can still restrict to the divisor and use induction on dimension. This is standard technique in algebraic geometry, but so in general, he cannot use it. So he considered mainly dimension 2 case. In the dimension 2 case, minimum model program still works. So you can contract -1 curve. And so this kind of process is allowed for non-Kähler complex surface. So, but already in dimension 3, so it is difficult. But if you assume Kähler condition, but then still you can extend some of the bilateral geometry. But in dimension 4 or more, there is no such a theory yet. So of course, algebraic case, there are more methods. But I mean, non-algebraic case is much more difficult. So so he has 2 kinds of method. The method 1 is complex analysis. So he solved elliptic PDE, and he used norm estimate and so on. So this was one method. Another method is more algebraic and geometric. And he used a sheaf cohomology theory systematically. He used exact sequence of sheaves and a long exact sequence attached to it and so on, and count dimension of the cohomology space. And this kind of algebraic method is systematically used. And I think he is one of the first people who use sheaf cohomology to geometry. So now it is a standard argument to use sheaf cohomology, but at that time it was a very new method. And also he used quotienting or covering and cut and paste, this kind of geometric argument. Okay, so this is the first part, harmonic analysis. So let X be a compact Kähler manifold and L be a holomorphic line bundle. So in the Kähler case, so there is Hodge decomposition theorem. So case cohomology group with coefficient C is decomposed into direct sum of HPQ, where HPQ is isomorphic to the cohomology group HQ of omega P. So this is holomorphic P form. But this HPQ is represented by harmonic forms. So this is defined by using Kähler metric. And he used also exponential sequence. So this is exact sequence of sheaves. So this is coherent sheaf, but these two are not coherent sheaf. But especially this one is only analytic sheaf. So this is algebraic, but this is not algebraic, algebraically defined sheaf. But anyway, by exponential from the structure sheaf to the non-zero holomorphic functions, that you have surjective map by exponential, so as a sheaf. And so of course this kind of exponential is surjective only locally, So you can use logarithmic function locally, but as a sheaf exact sequence, this kind of local to global so connection is so inside this sheaf theory, it is automatically involved. And then there is attached long exact sequence like this. So this one, so the first term is the group of line bundles. And this boundary map is to give the first Chern class. And this map is induced from the inclusion. So this is compatible with the projection, projection to the Hodge decomposition. Okay. So this is the first Chern class. So the first Chern class is in the intersection of second cohomology and H11. So now I define real 1-1 form to be positive if the coefficients define a positive definite Hermitian matrix at each point. And the line bundle is positive if the first Chern class is represented by a positive 1-1 form. And then this is the first theorem by so-called Codara Vanishing Theorem, proved in 1953. So if X is a compact scalar manifold of dimension n, and L is a positive holomorphic line bundle, then the piece cohomology group of the inverse of L is 0 if P is less than n. So usually Codara Vanishing Theorem is, so we use it for ample line bundle, but the original form is for positive line bundle. Actually, positive line bundle is automatically ample line bundle by the next theorem. But so the original form is like this, and it is proved in 5-page paper in Proceedings of National Academy of Science. It is a very short paper, and a lot of tensor calculus is involved in this paper. So first of all, these are remarks for the theorem. First of all, L is assumed to be positive, not ample, as I said, and the dual statement, cell dual statement, is also useful. So HP of L times canonical divisor. Canonical divisor is the highest holomorphic form. So sheaf of holomorphic forms of the highest degree. And this Codara Vanishing Theorem does not hold over positive characteristic field due to Reynolds example. And the statement of the vanishing is quite precise. So for example, if X is a projective space, then so K of X is minus n plus 1. So this so the homology vanishes if minus n or more. So if the degree is minus 1 and minus n or more, then vanish. And this is a very precise, very optimal thing. So on the other hand, self-vanishing theorem is very useful, but it is not so precise. So it holds to very generally. So X may have singularity and also arbitrary characteristic field or arbitrary projective scheme. But still, this is true, but this is not so precise. Yeah, but the cell is also very famous for promoting the sheaf cohomology theory so for example, coherent cohomology, coherent sheaf, and so on. Yeah, and they obtained the Fields Medal at the same Congress. So the proof of the vanishing theorem is like this. So of course I cannot prove this here, but this is just some remark. So this is an application of harmonic analysis. So D bar is defined on the holomorphic line bundle F, which is inverse of L. And the Dolbeau sequence can be extended in this way. So this is exact sequence of sheaves. And also harmonic analysis hold. So harmonic PQ form with coefficient in F is like this. So phi is a C infinity section of omega P tensor omega Q bar tensor F, such that D bar and D bar star are 0. So then suppose that the cohomology group does not vanish, then there exists phi, which is non-zero, and this should be represented by a harmonic 0p form with coefficient in L-1. And then it is expressed by tensor, and then Kodaira expressed some combination of the tensors, so and defined function which is positive, but the integral over the manifold is negative, and so the function is 0. So of course, this part is very much involved, and a lot of ideas necessary. But, so if you are interested, then please refer to this very short, look at this paper, because this is very short. Okay. So this is the application of Kodaira's vanishing theorem. So Codara embedding theorem proved in 54. So if X is a compact scalar manifold and omega is a scalar form, and assume that the scalar class, so this is in H2 by Hodge decomposition, but it is suppose that it is in the image of integral cohomology, then X is projective. So this is a criterion for projectivity of the manifold. And the proof is application of vanishing theorem in the following way. So first of all, the scalar form is correspond to line bundle. So this is called Lefschetz 1-1 theorem. So this is a long exact sequence coming from exponential sequence, and the omega comes from here, and so this is this one. So it is 1-1 form. So it equals to 0 here. Sorry. So omega comes from a line bundle here. So this is a very special case of Hodge conjecture, and very easy proof. But of course, Hodge conjecture is very hard in higher codimension. Now, so now I have a line bundle and take large number M and take a basis as basis of sections. So S0 to Sn, and define a rational map from X to a projective space by taking their ratios. So now the problem is reduced to prove that F is an embedding. And first of all, one has to prove that there is a base point, no base point. So that means there is no common zero of these sections. And then it follows that F is a morphism. And then this morphism separate points and separate infinite linear points. That means the sections, so if there are 2 points of X, then the values are independent. So these points are separated, and also infinitesimally the same thing happens. Okay. and these things are proved by using vanishing theorem. So first of all, so let's blow up these 2 points on X with exceptional divisors. So these points are replaced by n-1 dimensional projective spaces. And then there's a long short exact sequence of sheaves like this. Here I used additive notion instead of multiplicative notation. So for example, this is L to the power tensor power m is now written as m times L. So this is usual for algebraic geometry because we are using always divisors. So this is more easy. So this is also minus, it means tensor power ex minus 1. And then the long exact sequence attached to this short exact sequence become like this. And so the surjectivity of this map is the separation of point. And this is a consequence of the vanishing of H1 here. And also for infinitely linear points, vanishing of this one is sufficient. Yeah. And these vanishing are obtained exactly by the vanishing theorem. So now but by the way, are there any questions? Oh, okay, so I go on to next section. This is deformation theory of complex structures. Maybe this is the mostly referred result of Codara. Okay, so let X be a compact complex manifold and M be underlying differentiable manifold. And then so complex structure on X defines almost complex structure on M, J. So this is an action on the real vector bundle Tm such that J square is -1. So J corresponds to the action of multiplying the I, so the unit complex number. So and then the complexified tangent bundle is decomposed into 2 eigenspaces, Tx and T bar x, with eigenvalues I and -I. And so J corresponds to a subspace of subspace T bar x, because if you fix T bar, then T is just complex conjugate of T bar. So if T bar is so fixed, then it determines the almost complex structure. And the drum differential D is decomposed into 2 parts, round D and round D bar. And then a differentiable function H on M is holomorphic if and only if Cauchy-Riemann equation D bar H is 0. So D bar defines complex structure if it is integrable. Now, all small deformation of almost complex structure J is given by phi, which is differentiable section of T cross T bar star. T bar star is the dual vector bundle of T bar. This is equal to the differentiable section of homomorphism from T bar to T by this correspondence. So corresponding to phi, T bar phi is defined in this way, V plus phi V. So this T bar is modified by phi in this way. And then T phi is defined as a complex conjugate, and the drum differential decomposed in this way. So this is almost complex structure, and it becomes complex structure if it is integrable. And integrability is defined by this Maurer-Cartan equation. D bar phi is equal to half of D bar phi plus half phi D bracket is 0. So D bracket is defined in the following way. So that this holomorphic tangent part is multiplied by but this form is just sent identically like this. So this is a Maurer-Cartan equation which defines the integrability of this distribution. And then the complex structure is determined up to gauge action. So differentiable section of tangent space, exponential, one can define automorphism, and all the gauge orbit define the same complex structure. So more formally, one can say that the deformations are controlled by infinite dimensional differential graded Lie algebra. So this is for all degree P of differentiable sections of T. So 0P form valued tangent vectors. Of course, P is up to dimension of X. So there are only finite many degrees, but on the other hand, the sections are infinite dimensional. So this is infinite dimensional space, and by gauge action divided by infinite dimensional group action. And this defines the deformations or semi-universal deformations of X. So it is infinite dimensional, and it is, of course, one can treat this directly, but at the time of Codara, he took cohomology instead of DG algebra. So because if you take cohomology, then it is finite dimensional, and it is easier to handle. And he took Dolbeau cohomology group. So the cohomology group of this DG Lie algebra is a Dolbeau cohomology group, and they are finite dimensional. And the H1 cohomology group is a tangent space of semi-universal deformation, and H2 is the obstruction space for extending infinitesimal deformations in the following way. So infinitesimal deformation is defined in the following way. So where R is finite dimensional local algebra. So it is out in local ring with residual field C. So this is finite dimensional over vector space over C, which has ring structure, such that if one tensorize, so if one base change to C, then one gets original manifold. And then the tangent space is a set of deformations over the ring of dual numbers up to isomorphism. And this is isomorphic to H1. And the extension is like this. If you have infinitesimal deformation like this, and a surjective map of the parameter algebra such that this base change property holds, and this is called extension. And extension is not always possible, and it has obstruction H2. So this is so the formulation by Grothendieck after looking at Kodaira's papers. So Codara considered already this kind of thing, but it is formalized in this way by Grothendieck. So tangent space is H1. So Kodaira obtained this tangent space in the following way. So so let's cover X by small open polydiscs UI. And then the deformation of X is obtained by changing the gluing of these small pieces. So the intersection is denoted by Uij, then Ui on the and Uj glued along the overlap Uij, and the overlapping is slightly changed over ring of dual numbers, and the change is done by one cochain Vij. This is infinitesimal automorphism of the overlap. So if you change the overlap of two, yes? Excuse me?
You're just getting some feedback from Yao. You're all set now.
Oh, okay, thank you. So then if there are three polydiscs, then they should compatible. So these small shifts should be compatible, and this is written in the co-cycle condition. And so this is, and also this is up to co-boundary. This is corresponds to gauge group action. Yeah, Codara liked always this kind of with a lot of suffix. So yeah. Okay, and then the obstruction space is described in the following way. So I consider extension from the family of R to R prime, and assume that R prime is just one-dimensional extension. So the kernel is just one-dimensional. And then, first of all, each small open part, they are always extendable. And but the gluing is a problem. So overlap of two parts can be glued, but if you take three parts and glue, then one gets this kind of incompatibility, and this defines two cochain. But if the incompatibility is co-boundary, then the gluing pi_ij can be modified, and these small extensions can glue globally. So this is the obstruction. Okay. And now I go to the description of the semi-universal family. So semi-universal deformation is a smallest deformation family which contains all the deformations. So it doesn't satisfy universality condition, but it is almost universal. So it is called semi-universal. So first of all, the tangent space, I take basis and corresponding dual basis. And then I get tautological first order deformation, Phi1. And then I want to extend this second degree, third degree, and so on. This is formal deformation. So degree is counted by using the t's. So For example, phi 2 contains quadratic forms of TIs. And the Maurer-Kauta equation is solved inductively if the obstruction space vanishes. So Maurer-Kauta equation for phi is decomposed into infinitely many equations. And here, so d bar phi I for some I is expressed with phi j with, where j is smaller than I. So I can use induction. And inductively, phi I are determined. So I have to solve this elliptic differential equation. And it has solution with norm estimate, so a priori estimate. So the norm of the solution is smaller than the norm of the given function. So the infinite formal sum converges. So this is how Codara proved, Codara, Nirenberg, Spencer proved the following theorem in 1958. So assume that the obstruction space vanishes. Then there is a semi-universal deformation of X over an open polydisk inside the H1 homology space. So this is extended by Kuranishi to the case where the obstruction space is non-zero. In this case, the semi-universal family is not over all tangent space, but analytic subspace of tangent space. And the equation of the analytic subspace is given by Maurer-Kauta equation. Yeah. So is there any question? Okay. So now I want to consider deformation of submanifold of codimension 1 with fixed ambient space V. So the normal bundle is defined by the sequence. So the structure sheaf of the ambient space, and this is the space of holomorphic functions which has pole on X, and then the quotient space is the normal bundle. And in this case, the tangent space of the deformation of X inside V is H0 of the normal bundle, and the obstruction space is H1 of normal bundle. So if one consider the same theorem as in the previous slide, then if H1 is 0, then there is semi-universal family. But here, the theorem is better. So the submanifold X is called semi-regular if the map attached to this short exact sequence is 0. So for example, if H1 of normal bundle is 0, then it is, of course, 0 map, but it is a weaker condition. And then there's a theorem by completeness of characteristic system proved by Codara and Spencer in 59. It says that in the codimension 1 submanifold, suppose it is semi-regular, then there exists a family of submanifold which is universal at every point. So this is semi-universal deformation family. So this is a generalization of a result of Severi on curve on surface. But the result use sheaf theory and also analysis. So it is much more modern theory. And Kodaira asked a question. So even if the obstruction space does not vanish, there are many interesting examples like complex torus, where the semi-universal deformation is parameterized by an open polydisk in H1. So it is written in his lecture note, which I go back later. And it is developed to theory of unobstructed deformations. For example, Calabi-Yau manifold deformation is unobstructed due to Bogomolov, Tian, and Todorov. And Kodaira asked another question. Any scalar manifold has a small deformation which is projective or not. So it is proved in the case of surfaces by Kodaira, by classification. But so the counterexample is found by Voisin. Okay. So now I go to the next section. This is compact complex surfaces. So Kodaira said that a beautiful general theory is not interesting if there are no applications. And he looked always application. And these applications are mainly compact complex manifold of dimension 2. So first of all, I explain birational geometry. So the two algebraic varieties are two compact complex manifolds XY are birational if there are Zariski open subsets which are isomorphic. So the example is a blow-up along a smooth subvariety. And on the inverse direction, there's a Castelnuovo contraction. So let C be a curve on the surface which is isomorphic to projective line whose normal boundary has degree -1. It is called -1 curve. And Castelnuovo contraction theorem says that if there is a -1 curve, then there's a contraction from compact complex surface to another compact complex surface, such that the -1 curve is contracted to a point and otherwise isomorphic. So this is the inverse map of blow-up. And the compact complex surface is called minimal if there is no -1 curve. And always one can obtain this by applying Castelnuovo contractions finitely many times. And there's a theorem by Zariski and extended by Abramovich, Karu, Matsuki, Wlodarczyk. So if F is a birational map between compact, actually algebraic, compact algebraic, so smooth projective algebraic varieties. So sorry, here X and Y are smooth projective algebraic varieties. And if they are birational, then they are connected by a composition of blow-ups and blow-downs. And Zariski proved it in the case of dimension 2, and AKMW proved in general. So this is birational geometry. And then in birational geometry, birational invariants are important. So they are numbers which are independent of birational models. So first one is Purely genus, M genus of X. This is dimension of MKX. And this is P irregularity, so number of P holomorphic P forms. And this is kind of dual thing, number, so a P-score homology of O, but they are not equal. So this one and this one are not necessarily equal if the manifold is not scalar. And the difference is important. Or also positive characteristic case, they may be different. And the Codara dimension is the growth rate of the Purely genus. Now the problem is to classify all minimal compact complex surfaces or a birational classification of using birational invariants. And this was done by Italian school, Enriquez, Castelnuovo, and so on algebraic surfaces. And Codara extended this to non-algebraic and non-scalar surfaces. And the method, important method is to use divisor. The divisor is a formal combination of codimension 1 subvariety, so curves with integer coefficients. And they are called linearly equivalent if the corresponding line bundles are isomorphic. And the method of a linear system is important. So the linear system corresponds to a linear subspace of the space of sections. And this is finite dimensional projective space. So this is quite geometric. So algebraic, this is itself an algebraic variety, and one can use induction on dimension. So, and complete linear system corresponds to the whole space of the sections. So for a given linear system, if I take a basis, then I get a rational map to a projective space if I take the ratios. And this is not well defined when all the sections vanish. But if the linear system does not have base point, then this becomes a morphism, so everywhere defined. And the important numerical number is this holomorphic Euler characteristic, the alternating sum of the dimension of cohomology. The dimension of the cohomology is quite difficult because it is not deformation invariant. So if I deform D a little bit, then the dimension jumps, but Euler characteristic does not change. So it is more reliable number. And the canonical divisor is quite important in the classification. And Codara proved Riemann theorem in the following way. So this is 1951. So he proved it for compact complex manifold surface, which has a divisor. So of course, compact complex surface does not necessarily have a divisor, but if you have a divisor, then you can use this Riemann theorem. And this is generalized by Hirzebruch, Artier, Singer, and so on. So this is one of the most important theorems in algebraic geometry. And he used also Noether's formula, which express the holomorphic Euler characteristic by this is first chunk class, second chunk class. And cell duality is also used a lot. The first problem is the rationality criterion. This is due to Castelnuovo. So a surface is called, algebraic surface is called rational. It is birational to projective plane. And so suppose that X is algebraic surface whose second genus and irregularity vanish, then it is rational. So this is a very striking theorem, and that is the origin of many important development later. And Codara tried to give new proofs of this theorem. So I heard that he made many proofs using sheaf cohomology. So of course, Castelnuovo did not know sheaf cohomology, so his argument is much more involved. But Codara gave a much streamlined proof by using sheaf cohomology. And in his proof, he considered a joint system. So if you have a divisor, then D plus K is called a joint system. And so adjunction terminates. This is traditional Italian expression. So D plus MK is vanish eventually for very large M. So this is so-called adjunction terminates case. And Codara considered this case and found some structure like existence of -1 curve and so on. So this was a method of proving Castelnuovo criterion. In the modern modern language, so adjunction terminates is replaced by the following thing. So not only d plus mk, but so m is here, m is always integer. But modern language, it is called rational or even real number. And so for h ample divisor, take h plus tk, and also one consider the numerical effective. So the linear system is, if the linear system is non-empty, it is called effective. But we consider numerical effective. And the biggest number is called Neff threshold. Yeah. And then take Neff threshold. So one can say prove that the Neff threshold is rational, and then take large multiple of it, and then this is Neff linear system and become base point free and defines Castelnuovo's contraction and so on. So this kind of argument is generalized to higher dimension in minimal model theory. So next topic is K3 surface. K3 is named after Kunihiko Kodaira by Andre Weyl. K3 is the surface which has a trivial canonical bundle and vanishing irregularity. And traditionally, it was known that there are infinitely many 19-dimensional families of algebraic K3 surfaces. So each even positive integer d, there's one family of 19-dimensional algebraic K3. So d is the amplitude square of polarization. So degree 2 is the double curve of P2 by curves of degree 6, ramified along curve of degree 6. Degree 4, K3 is a hypersurface of degree 4. Degree 6 is complete intersection of degree 2 and 3. And degree 8 is 2 complete intersection. And the higher degree cases are no more complete intersection. But Codara proved that there is only one 20-dimensional family of K3 surfaces, which are proved Kera later by other people. So Codara proved in 1966 that there is only one family connected by deformations. For example, the cortex surface, so degree 4 K3 has only 19 dimensions, but it deforms out of P3. And generic member in this 20-dimensional family is no more algebraic. So general K3 surfaces have no equations. So it is impossible for algebraic geometers because they are not algebraic surface, but only Kera surface. No equations are possible. So in this case, the deformation space, so tangent space H1 is 20-dimensional, and the obstruction space vanish. But algebraic case, so algebraic K3 has polarization L, so ample divisor L, and the algebraic family preserves this polarization. And this condition is equivalent to this. So the deformation direction is orthogonal to the first Chern class of the polarization. So this is 19-dimensional. And there are infinitely many 19-dimensional subfamily inside 20-dimensional. And it is dense. So it is very complicated. So that 20-dimensional smooth space inside 19-dimensional hypersurface, but they are dense. And actually, so Kuma surface is a special case of algebraic surface. So this is a desingularization of the quotient of abelian surface by involution. And Kuma surface are dense in the moduli space of K3. So if you take any K3 and any small deformation, then inside in this deformation family, there are infinitely many Kuma surface. So in this way, Codara proved the connectedness of the deformation family. And later, global Torelli theorem is proved. So this is not Kodara's work. So moduli space of K3 surfaces is equal to the period domain. So period domain is the moduli space of Hodge structures. So there is, so I don't state this theorem more precisely, but the statement of the theorem is very precise, and it is factorial also. And so, for example, even the automorphism group of each individual K3 surface is also determined by this global Torelli theorem. So it is a very factorial theorem. And so this is bijectivity. So injectivity is proved by Piasecki, Shapiro, Shafarevich in 1971 in algebraic case, and Burns-Rappaport in more general case. And surjectivity is proved by Todorov using a twistor family, using Yau's Kähler-Einstein metric. So now Kodaira asked if, so the compact complex surface X is scalar if and only if the first Betti number is even. So this question is looks very strange. Anyway, if it is scalar, then B1 is even because Hodge decomposition theorem. But the converse is very difficult, and it relies on the classification of the surfaces. And in the elliptic surface case, it is proved by Miyaoka's master thesis in '74. This is a 4-page paper in Proceedings of Japan Academy. So this journal is usually only specialized on the summary, but this is the complete proof. And later, Hsu proved in '83 that all K3 surfaces are scalar, and in this way, Kodara's question is confirmed. So now I go to elliptic surface. Elliptic surface is so this morphism from surface to curve, and the general fibers are elliptic curves. And Codara classified fibers, singular fibers. So 1,0 is a regular fiber, so this is not singular, but others are singular fibers. So he classified all the singular fibers of elliptic surface in the following way. They appear only on minimal elliptic surface. So that I assume that there is no -1 carbon in the fiber. Then there are singular fibers 1B, M1B, 2, 3, 4, and 1 star, 2 star, 3 star, 4 star. 1,0 is regular, and 1,1 is a rational curve with one node, and other 1B cycle of B smooth rational curves. And M1B is multiple fiber. So scheme-theoretic fiber is M times 1B. So this is the only multiple fiber. Others are all reduced, not reduced, but there is no GCD of the multiplicities. And 2 is a rational curve with one cusp. 3 is 2 smooth rational curves tangent at one point. 4, 3 smooth rational curves meeting at one point. And then 1 star, 2 star, 3 star, 4 star, all a tree of smooth rational curves. And these Roman numerals are Kodaira's notation, and the Dinkin diagram notation is this. So 1b is equal to a tilde b minus 1, and 1b star is d tilde b plus 4, 2 stars e tilde 8, and so on. And this Dinkin diagram is here. So these dots are smooth rational curve, and these edges are intersection, transversal intersection. And if I remove one vertex here, then I get dn minus 1. And dn tilde is tilde means one vertex is added. So E6, I should remove this. E7, I should remove this. And E8, I should remove this. So this kind of Dinkin diagram appears in many corners of mathematics, and they are related and very interesting. And Codara proved canonical bundle formula. The canonical divisor of the total space is equal to the pullback of something plus term coming from multiple fibers. So these mi are multiplicity of the fiber. So this is mi bi. Okay. And so what is D? So D is a divisor on the base curve whose degree is equal to this. So this is a 1 over 12 of the sum of the numbers ni, where ni is almost equal to these Roman numbers. But these are just 12 minus Roman numbers. And the 1b star is in the middle. And bi is, these come from I1bi. Yeah. So this 12 is the denominator of Netter's formula. And actually this degree is proved by using Netter's formula. And 12 is also equal to the degree of the automorphic function, delta. This is the denominator of the J function. And J function has poles of order bi at IBI singular fiber. And the D12 is also the least common multiple of the order of automorphism, group automorphism of elliptic curve. And these number ni are also eigenvalue of the local monodromy of the H1. So they are all related and very explicit. So Kodaira classified elliptic surface, and he described in detail and constructed elliptic surfaces using J function of the fiber, monodromy of the first cohomology, and torsor action and action under the elliptic. So this is a group structure, so there's torsor. And in order to deal with multiple fibers, he constructed so-called logarithmic transformation. This is a totally non-algebraic method. So summing up, I can say that elliptic surfaces are well understood by these results. So now Kodaira, this is a table of Kodaira's classification of surfaces. So from 1, 0, 2, 0, 3, 0, and 7, 0. 0 means minimal. So if you blow up these surfaces, then you get 1, 2, 3, 4, and so on. So first 5 are scalar surfaces. And the last two are non-scalar surfaces. And K3 surfaces and complex torus are 2 and 3. And so these are very explicit. And also elliptic surfaces are well understood. And these are characterized by using these birational invariants. But so the first one, algebraic surface, and the fifth one and the seventh are not so precise. For example, the first one, the case where the geometric genus is trivial. This is a very interesting class. So contains fake projective plane, for example. So fake projective plane is very similar to projective plane, but general type. So they are contained in this class, and a lot of research is done. Also recent, there are many recent results on this class. And of course, general type is quite open. So there are too many surfaces. So they are also interesting. Actually, this one, so many of the surfaces in the class 1 are general type. So the general type is quite wide. Yeah. But Kodaira was interested in 7-0 surface. So this is non-scalar surface, so especially interesting. And he considered Hopf surface as an example. So Hopf surface is a surface whose universal covering is C2 minus origin. For example, if this is so the quotient surface by infinite cyclic group by Z1, Z2 go to alpha 1, Z1, alpha 2, Z2, where alpha 1 and alpha 2 complex numbers. So it is like this. So it is an elliptic surface if these coefficients are proportional in algebraic way. Otherwise, there are only two curves on this surface. So there are many surfaces which have no curve, but in this example, there are two curves. In the elliptic surface, there are infinitely many curves. And Codara proved that a surface is homeomorphic to S1 cross S3, then it is Hopf surface automatically. Hopf surface is a surface whose universal covering is given. And this 7-0 surface attracted a lot of people. So this Inoue, Kato, Nakamura are students of Kodaira, but also Bogomolov have important contributions. So related question like, is there a complex structure on S6 is a very dangerous question, but it attracts a lot of famous mathematicians also. So because there are no almost complex structures except S2 and S6. So anyway, S6 cannot be Kähler threefold. So it is very difficult. Okay, this is the end of mathematical works of Kodaira. So are there any questions?
Yeah, I think there are some question. There are some question in this Q&A.
Yes. So
you can see.
yeah. Yeah, the first question is, at the beginning of his career, Kodaira worked on eigenfunction expansion of Sturm-Liouville theory, generalizing Weyl's work, which is in classical analysis. What motivated him to change the direction into complex manifold? Actually, I'm not sure. So I'm very sorry. I'm not sure that his early works. Sorry, maybe other people know better. So second question is that the Kodaira's classification of degenerate fiber of elliptic fibration is parallel to Néron's integral model of elliptic curves. Are they motivated from each other or they are independent? Oh, this is also a difficult question. So I know Néron's work, and maybe they are independent, but I'm not sure. I'm not sure. So sorry. I'm actually I talked to Kodaira several times, but I did not ask this kind of question. So I was very ignorant. Yeah, sorry. So maybe I cannot take any question. I cannot answer. But anyway, I tried to answer some kind of question if I can answer. But are there more questions? So is this all?
Yeah. Oh, yeah. So
this is all.
I have one question. You finished or not yet? So I have one.
Hello?
Hello?
Let's do a question about Kodaira's Class 7 seal. Class 7 seal. Kodaira's work on the non-tailored surface. Class 7 seal.
Class 7-0, yes.
So Kodaira believe those examples given by Inouye and himself, I guess also Bombiali, exhaust all the examples?
This is a hard question. So, yeah, so maybe not, but I don't know. I don't know. Yeah, so.
He must have thought about this problem after he went back to Japan, right? He must have put in a lot of work in this problem after he went back to Japan.
Yes. So that's why many of his students tried to solve this question. But after a while, it became clearer that it is harder problem than originally expected, I think. So
also, when Kodaira did the work on Hodge theory, did he know much about Hodge's work because it was during the wartime?
So so of course all the results are known, but so in the worst years of the war, no paper came in. So the results proved in the last years of wartime, Kodaira had no knowledge. But I think there are more works before that, and I think he knew that. So he was always looking at the journal papers. So if it was available, then I think he knew that.
Also, after he graduated in 1938 in mathematics, why did he go to physics?
Yeah, this is a question, but I think at that time it was a difficult time at the university, and so the job was also not so clear, but also many students went to war, and yeah.
He want to avoid going to war himself, or
maybe he was a little bit older than that generation, but still, so I think that situation in the university was not the same as these days. So, but I do not ask him directly. So this is only my guess. So, anyway, the system was not so rigid like these days, and also mathematics and physics were much closer at that time. This is another reason, I think.
What kind of physics did he study?
I don't know. Sorry. Sorry. Yeah, there are a lot more to be investigated, I think. Yeah.
Also, when he studied non-algebraic surfaces, was it motivated because of Atiyah-Singer index formula holds for non-Taylor surface?
Yeah, so yeah, at that time, I think Taylor or algebraic, so such restrictions are not so natural, because for Riemann surface, there is no such restrictions. And yeah, at that time, so I think the entrance is wider. So these days, people assume projectivity or something at the beginning, but I think at that time, people considered not in that way. So yeah.
So my question is that was the index theorem Riemann law for non-Taylor surface?
Yeah,
independent
yes.
Atiyah-Singer formula?
Yeah, but the Riemann rock works only for divisors. So if there is no divisor, then it doesn't help at all. But yeah. Anyway, Codara's proof is very direct. So if there is one divisor, then you can get this Riemann rock theorem. So sometimes non-Taylor surface has divisor, so one can use that divisor to study the surface.
So he does need to use Atiyah-Singer index formula.
Yeah. Okay. So I have still some sections. So can I go on?
Yeah, go on.
Yeah.
Yeah, go on.
So now I'd like to explain his lecture notes. So this is lecture notes published in the Department of Mathematics in Tokyo. And these are handwritten lecture notes of graduate courses given at the University of Tokyo, which is at the time of student movement. And these are in Japanese and with a lot of drawings and reproduced by mimeograph. And the notes are taken by his students. So he wrote five lecture notes, and so these are volume numbers. So there are other lecture notes by other professors. So the first one is Deformation Theory 1, so 99 pages, Algebraic Surface, 89 pages, and Deformation 2, 303 pages. This is much thicker written by Horikawa. So Horikawa tried to explain more than Kodaira did, I think. And complex analytic surfaces. And the last one is Nevalina theory. And this is translated into English by Osawa, but others are not, I think. And so when I was a student, I studied algebraic geometry using these lecture notes. And these are very concise and very nice very nice material for students. And so there's some selected words by Codara. So he said, maybe there is a sense of mathematics besides 5 basic senses. In order to develop this sense, one has to work hard, read repeatedly proofs of known theorems, write them down in notebooks, think about them long hours, and try to apply them in examples, and digest, decompose into pieces, and reconstruct, like taking nutrition. A correct proof is natural and appears straightforward, but is not boring because there are ideas. I happen to find many theorems, but they seem to be already there. If I did not find them, then someone else would have found them. So Kodaira talked sustained. Yeah, thank you very much. So this is the end of my talk.
And do you think those books
Thank you.
translate into English for people to read?
No, these are my translations. So it is a poor translation. Actually, he spoke in Japanese.
Okay. Can we find some people to translate it so that people can read? He's a good writer.
Yes?
You think we can find some people to translate it who has the right, publishing right to translate those books?
Books? You mean lecture notes?
Yeah, lecture notes.
These are, I think it is quite so kind of private, so unofficial publication.
Yeah.
So I think if you want to translate, then I think, yeah, of course, one has to get permission from the math department, but I think there will be no problem. So mathematics department has a right, I think.
I see. The Department of Tokyo, University of Tokyo?
Yes.
Okay, maybe we should try to do that. So I was told that Kodaira wrote a lot of textbooks for high school. Is it true?
Yes. But this is a little bit different system. So textbook is usually written by group of people, and so Kodaira was a chairman of one of the committee. So I mean, every publisher organize a committee, and there are a lot of high school teachers and so on. So Codara jointly wrote textbook with them, and yeah. So I cannot say which part is written by Kodaira, but maybe some part. But anyway, so Kodaira's philosophy, his way of thinking was projected to other members and in the textbook.
Are they good textbooks?
Yeah. So actually, I did not read the textbook by myself. So sorry. Yeah.
Are they still there? Can one find copies?
I think so. Yeah. But yeah, maybe. Yeah.
I would be interested to see it.
Yeah. This is a special system, so that the textbooks are published by several publishers, and they should submit to the government to get approval, and so government officials, so the Ministry of Education people, correct or change the content. So I mean, they suggest to change, and the authors should change, and so on, and then the textbook is approved, and then the schools, each school district choose which textbook is used and so on. So there are a lot of people involved in textbook making. So this is not free thing to write. And also the textbook should follow the instruction. First of all, the content, what kind of thing is involved and so on, should be already determined by the ministry. So they cannot change much from the content. Of course, the way of explaining things are free, but somehow the contents of the textbooks are similar in some sense.
That would be nice to translate it, I think.
Okay, so are there any more questions? So I have one question on Kodaira has a problem. He asked for deform Keller to projective manifolds. So in damping 2 is solved by himself, and damping 3 is already okay. And damping 4 there are some counterexamples by Graf-Voisin. And so I'm wondering if it's possible to consider deformation to singular projective varieties. Because in this example, they only consider smooth projective varieties. So yeah, I don't. Does it make sense to consider such problem?
Yes. So, and also I think some birational. So Voisin made also counterexample to birational class. Yeah.
So okay. Then this could also give a counterexample.
Yeah. So yeah.
Okay.
But anyway, some kind of modified statement is, I think, it will be useful. But yeah.
Okay. So another question is, you talk about this. If the first Betty number is even, then the surface must be Keller.
Yes.
And then you mentioned that they work on Miyaka on elliptic surface and also show on K3 surfaces. So what about other surfaces? Other surfaces are well known? Or?
I think other surfaces are treated by Codara.
Okay. So this problem is completely proved. Okay.
Yes.
Okay, thank you.
Actually, talking about that, the class 70 Bogomol's argument is not clear to all people that I know about class 70 case 1. Only later, when Jun Lee and I and Chen use Hamiltonian mills, we figure out the proof correctly. The case when Kodaira 770 has no curve, that was that was proof to be the only known samples on Inouye surfaces. But that proof is not far away from clear in Bogomol's argument.
Yeah, so 70 surface is a very important subject. Still, still missing some important thing. So, yeah, it's a very mysterious surface. Yeah, and also many great mathematicians try to solve it, but still it's open.
That's a beautiful talk. Thank you.
Okay, thank you. Okay, thank you. Okay.
Thank you very much.
Thank you very much.
Thank you.
Hope to see you in Beijing sometime.
Next year.
Yeah, next year. Yeah.
Okay.
Thank you. Okay, bye-bye.
Yeah, bye-bye.
Okay. Bye-bye.